Welcome students to the ongoing discussion on the non-resonant charged particle induced reactions. So, let me take a quick review of the previous class. Though the PPT title is same for the previous lecture and today's lecture. So, in the last lecture I have provided enough background to understand the concept of charged particle induced non-resonant reactions. Okay. So, in the last lecture what I have done, I have considered a proton plus proton reaction, which is one of the most fundamental nuclear reactions responsible for the nucleosynthesis and also the evolution of universe, we can say, and the importance of tunneling, right, and what kind of arguments I had given. I hope you have followed it. Let me quickly present before you again. The Coulomb barrier for proton plus proton is 550 keV around, and classically the fusion can happen only when the temperature corresponding to this 550 keV is available. It is like 10 to the power of 9 kelvins, and the argument went like this: if the star has a temperature of 10 to the power of 9 kelvins, and before that if no nuclear reaction occurs, the moment 10 to the power of 9 Kelvin temperature is reached, then all protons will react with each other immediately, and one can expect catastrophic explosion, which is not happening practically. So, that clearly indicates that before reaching the temperature required for classically nuclear reaction happens, the fusion is indeed happening. What could be the reason at that particular temperature? So, people have given argument like, no, with that Maxwell-Boltzmann distribution at the high tail end at a particular temperature. So, consider the particles at a high energy range, high energy tail end, and if high energy is available, then it is okay, fusion can happen. Sounds bit good, but one has to also see whether the number of particles at high energy tail end is sufficient to account for the energy production, and we have seen it was 10 to the power of minus 275. The ratio of probability for the particles to have 550 keV and to have 0.86 keV corresponding to this less temperature like 0.01 gigakelvin. We have seen 10 to the power of minus 275. So, that is not sufficient. It is inadequate to account for the energy production in stars. All right. Then it was a major obstacle, even though Eddington had suggested that very high density available in the sun and other stars, the fusion could be responsible for the energy production. That argument could not be supported by the mechanism of reaction, but when Gamow and others independently who proposed that below Coulomb barrier also there is a finite chance for the charged particles to come out of the nucleus or to enter the nucleus, so called quantum tunneling process. After that, people could confirm that it is because of the quantum tunneling process fusion reaction is taking place. And to support this, I have presented few things like, let me quickly repeat those formulas, okay, and then I will cover astrophysical S-factor and the concept of Gamow peak. Okay. So, in today's lecture I am going to give a final touch to this P plus P reaction, and S-factor concept I am going to discuss, and Gamow peak concept. Okay. So, same questions which I have posed in the previous class, that is, because cross section depends on the energy, is it possible to avoid, and at different energies if reactions are induced by charged particles, how to identify the range of energies over which maximum number of reactions take place, and is it possible to estimate the most effective energy at which nuclear reaction take place. And the most striking feature is the dependence of reaction rate on the temperature of a star. Okay. Now, going back to this P plus P reaction, proton plus proton, quantum mechanically you know square of the wave function at nuclear radius is nothing but the probability of the probability for finding the particle at a nuclear radius is this one. Okay. This one tells us the probability of finding the particle at a nuclear radius, and this one the probability of finding the particle at classical radius, at classical radius. In the previous lecture, I have denoted the locations of nuclear radius and classical turning point. Fine. Now, solving the Schrodinger equation for the Coulomb potential, you can arrive to this equation, the probability exponentially minus 2k classical turning point, tan inverse and remaining expression. Okay. Now, here the expression for k is given like this. Fine. Up to this I have discussed in the last class. Continuing this, let me introduce one of the most important parameter in nuclear astrophysics. Okay. Now, at low energies, that is less than Coulomb barrier, at low energies where the classical turning point is much less than the nuclear turning point, this equation can be approximated by writing like this. Okay. Same probability exponential, the approximation goes like this. I am not going into the details, and this I can represent as 2 pi Sommerfeld parameter. Okay. And this e to power of minus 2 pi eta is called as Gamow factor. Gamow factor. What is the importance of this Gamow factor? It considers the effect of quantum tunneling process at low energies of charged particles, at low energies of charged particles. Okay. So, the Gamow factor tells us the exponential dependence of the probability, where eta is Sommerfeld parameter, and if you express the same quantity numerically, the 2 pi eta, you can derive yourself without any problem, where E is in keV and mu, that is reduced mass, in AMU. So, this value is important while calculating the Gamow factor. Fine. Now, after introducing the Gamow factor, let me introduce the cross section formula. This cross section, which depends on the energy for charged particle induced non-resonant reactions. I am talking about non-resonant reactions induced by charged particle, non-resonant reactions induced by charged particles. See, cross section anyway it depends on e to power of minus 2 pi eta, I have discussed already, and earlier if you remember, replacing classical area pi r square with pi lambda square. Do you remember? When I have discussed inverse reactions and forward reaction, I have provided a general formula for the cross section of a nuclear reaction. What were those 4 terms? Pi lambda prime square, which consists of de Broglie wavelength, replacing the classical radius with the de Broglie wavelength. Number 2, statistical factor. Number 3, identicalness in terms of Kronecker symbol. Number 4, matrix elements, which represents the nature of interactions in the entrance channel and in the exit channel, isn't it? So, then at that time I have discussed the representation of cross section in terms of lambda prime, that is de Broglie wavelength, isn't it? So, lambda prime is nothing but, in terms of energy, you can always write down as 1 by E, right. So, lambda square is basically 1 by E. So, that 1 by E is represented here, isn't it? So, let me erase this to avoid any confusion. Great. So, 1 by E dependence you know on cross section, because as energy decreases below the Coulomb barrier, cross section decreases. Okay. And Gamow factor already I have introduced, isn't it? And sorry, it is other way around. As energy increases, the cross section is happening in other way, and this is Gamow factor, which takes into account the effect of quantum tunneling, and this astrophysical S-factor, this term S-factor considers all nuclear effects. Okay. So, for non-resonant reactions induced by charged particles, the cross section consists of 3 terms. Number 1, 1 by E, okay, and number 2, Gamow factor, and then S factor, astrophysical S factor, which contains all nuclear effects. Okay. So, our understanding of non-resonant nuclear reactions, where cross section is a smooth variation of energy, Later I will separately discuss resonant reactions, where cross section will have sudden change at particular values of energy. So, that I will discuss later. Right now the assumption is that cross section is smooth function of energy, smooth function of energy, isn't it? So, these three terms we are going to use extensively, and we are going to rework on the reaction rate equations. Fine. Now, how cross section varies smoothly above the Coulomb barrier, okay, and it drops below Coulomb barrier due to transmission probability, okay, and astrophysical S-factor. This reduces the energy dependence, because by multiplying E with sigma, you can always write down the expression for astrophysical S-factor. Now, here let me give you one good example how to understand the relation between cross section and the S-factor. Okay. So, above Coulomb barrier, the cross section is varying smoothly. For this reaction of proton with oxygen 16, the Coulomb barrier is about 2.2 MeV, and the moment you go down to the Coulomb barrier, the cross section is decreasing, because the classical level probability is coming down, because it is the energy is below the Coulomb barrier, and it is because of the tunneling process, and the tunneling probability decreases with decrease in energy, right. See how cross section is varying from 10 to the power of minus 11 to 10 to the power of minus 10, sorry minus 6, so much variation. Now, if you want to find out the cross section at low values of energy, then one needs to extrapolate this cross section, and this extrapolation of cross section induces a lot of error if there is a huge change in the y axis value for small change in the x axis value. In most of the cases, the Gamow peak energy values are not available in Earth's laboratory, I mean except very few facilities in the world. So, people always prefers to go for extrapolation kind of work, and if you depend on cross section dependent energy, then extrapolation induces lot of uncertainty. That is where the significance of astrophysical S-factor comes into picture. How? See the second diagram. If S-factor is plotted whose units are keV barn versus center of mass energy, you see the variation is not very high, and remember this is a logarithmic scale, and this is a linear scale, isn't it? So, even at linear scale the change is not very high for this particular energy, proton induced radiative capture reaction with oxygen 16. So, the S-factor basically reduces the energy dependence, and this is where extrapolation is more reliable when compared to cross section. I hope it is clear to you. Okay? And for charged particle induced reactions, this reaction rate expression is well known to you, where mu is the reduced mass, this kT is a well known parameter, energy, cross section, and e to the power of minus e by kT. How you are why are you using this word in this expression? Because of the Maxwell-Boltzmann distribution. Now, I am going to discuss one of the most fascinating and interesting aspect of nuclear astrophysics, when charged particles are playing role in terms of energy production from the stars and nucleosynthesis. So, please pay attention to this mathematical treatment, all right. So, this discussion I am starting with the well known expression for nuclear reaction rate, which considers energy dependent cross section and the Maxwell-Boltzmann distribution of the particles, because they are non-degenerate, though they are fermions. We are using Maxwell-Boltzmann distribution. Please recollect the previous discussion, that is Gamow factor and S-factor, how that expression is useful in this reaction rate formula. Let me go one after the other. Okay? Now, let me express this reaction rate formula in terms of S-factor, that is cross section I have already written S-factor e to the power of minus 2 by eta and energy. So, substitute this here, substitute this expression of cross section in the expression of reaction rate, because reaction rate cannot be calculated without the information of cross section, and this cross section has 3 terms, remember, and each and every term the significance you need to be clear about it. Now, I am going to write the reaction rate by using this terminology of S factor. Okay. You see e to power of minus 2 pi eta in terms of sigma, okay, 1 by E and E they got cancelled, fine, and S of E is there, rest remains as it is. Okay. So, this is the reaction rate for a non-resonant reaction induced by charged particles, not resonant reaction, fine. Now, here the value of kT already I have given in one of the previous lectures. In terms of gigakelvins, it is 0.086, 0.086 T9 in terms of MeV. Okay. Now, here please analyze, e to power of minus E by kT approaches 0 for large energies, approaches 0 for large energies, isn't it? Whereas, e to power of minus 2 pi eta approaches 0 for small energies. In the integrand, please observe there are 2 exponential terms. What are those 2 exponential terms? E to power of minus 2 pi eta, which came from the tunneling phenomenon, and e to power of minus E by kT, which came because of the distribution of the energies of particles at a specific temperature T. When these 2 exponential terms are there within the integrand, can you guess what the product of these 2 exponentials gives us? What kind of information the product of these 2 exponential terms gives us? That is very interesting, and in terms of some diagram, let me try to explain. Okay. Now, here if you see the tunneling probability, finally all types of probability I am expressing here, the tunneling probability increases with increase in the energy, okay, and finally after Coulomb barrier there is no tunneling. However, according to this Maxwell-Boltzmann distribution, you have e to power of minus E by kT. Okay. This is much sharper, not so much broader. Okay. So, you can see very sharp initially, and then you can see it is going like this, isn't it? This is energy. Now, the product of these 2 gives rise to a beautiful peak, okay, where the centroid is E naught and the kT is somewhere here, remember. Okay. The product, this is e to power of minus 2 pi eta, and this is e to power of minus E by kT, E by kT. Remember, this eta contains the energy term. Please look into the formula for Sommerfeld parameter, fine. The product of this is this one, isn't it? So, this is called as Gamow peak. That means, the peak denotes an area or the region about which the most of the nuclear reactions are taking place. This is the answer for one of the questions. The first question which I have asked in one of the previous slides was how to reduce the or how to avoid the energy dependence of cross section using S factor. Second question was at what energy range most of the nuclear reactions take place. This range can be calculated easily by taking the product of 2 terms, e to power of minus 2 pi eta and e to power of minus E by kT. So, let us see the salient features of this peak, which is called as Gamow peak. Okay. Now, for those values of energy, when the product of both factors is near its maximum, that is where major contribution to the integral comes into picture, and it results into a sharp narrow peak in linear scale. I am talking about in linear scale, which we are calling as Gamow peak. All right. Now, the centroid of the Gamow peak is E naught, and this is always greater than the maximum of Maxwell-Boltzmann distribution kT. Please understand the relation between E naught and kT. Okay. Here, let me give you one example, okay, where in logarithmic scale, if I draw e to power of minus E by kT, it will be some kind of straight line, and e to power of minus 2 pi eta exponential increasing, and the product e to power of minus E by kT and minus 2 pi eta is nothing but some kind of peak. Please remember, this is in logarithmic scale on y axis. The same thing if I plot in linear scale for a particular reaction, okay, it is about 0.32 MeV, that is 320 keV. Fine. You see the location of kT and you see the location of E naught. Okay. And here you can see the dotted line is approximate one and the solid line is exact one. So, this peak is not exactly Gaussian, it is very close to Gaussian. I will explain more about this in due course. The point which you have to understand here is the product of these two quantities decides the energy range over which maximum number of nuclear reactions are indeed taking place within the stars. How does it matter? When you want to understand the energy produced from a star because of a particular nuclear reaction, at what energy range you will carry out the measurement? This Gamow peak will help us to decide the energy range. Okay. Now, here I have taken an example of carbon 12, okay, all induced by alpha radiative capture reaction, 16 oxygen stable isotope. Okay. So, the maximum of Maxwell-Boltzmann distribution, if you see, the kT is 17 keV only, fine, whereas it is 320 keV for the centroid of the Gamow peak. So, earlier when you have drawn the Maxwell-Boltzmann distribution, the maximum when it comes at kT, you might have thought the maximum reactions are taking place at that value of kT. No. For charged particle induced non-resonant reaction, the maximum reactions are not taking place at kT, but at some other energy which is higher than kT. That we are denoting using a symbol E naught. Okay. Now, the high energy tail of the Maxwell-Boltzmann distribution, most of the reactions occur. So, the reactions are not occurring at the peak area of the Maxwell-Boltzmann distribution, but high energy tail of the Maxwell-Boltzmann distribution, the most of the reactions are occurring. Now, this narrow energy range over which most nuclear reactions are taking place, I am using the word Gamow peak. Okay. Once we have this Gamow peak in our mind, several questions should come to our mind. See, the moment you say Gamow peak, the centroid, the value at y-axis corresponding to the centroid, that is maximum of the integrand, and the area of the peak and width of the peak. Because in today's lecture I am using all these parameters. Initially it may look like confusing, but it is very simple to understand, just you have to be little patient to relate various parameters. So, most of the mathematics I am doing in today's lecture requires derivation from your side as part of homework. Okay. So, I am very happy to introduce a few questions related to Gamow peak. I hope this will help you in understanding the concept of non-resonant nuclear reactions and how reaction rate is depending on various parameters. Finally, we have to come up with temperature dependence, because at that temperature which is frequently changing in the star, reaction rate is also changing, and we are in process of obtaining analytical expression for reaction rate at different values of temperature. All right. So, what is the list of questions? Have a look. How to calculate this centroid of the peak? Just qualitatively I have shown you the location of E naught. Now, how to calculate the width of the peak also? Fine. And how this centroid and peak width depends on the charge of the target and projectile, and also on temperature. Third question, the peak area, does it vary when the charge of the target and projectile changes? If yes, what is the analytical expression for that? We have to derive. Now, whether the peak width, which is also in terms of energy, is greater than the value of the centroid or less than the centroid, okay, that we need to understand. And with respect to the Coulomb barrier, how the centroid of the peak and the peak width changes, this we need to understand. All right, let us see. And also the maximum intensity of the peak is related to Vc. See, this peak, Gamow peak, okay, this is the probability and this is the energy. This maximum, I am talking about this maximum, okay, how it varies with respect to the Coulomb barrier of the nuclear reaction. All right. The first question, let us take to calculate the centroid, The simple way is take the first derivative of the integrand. This integrand involves two terms, e to the power of minus 2 pi eta and e to the power of minus e by kt. Okay? Take its first derivative equal to 0, that gives you the value of energy at which maximum probability is occurring. Energy at which maximum probability is occurring. Fine. And equating to 0, after taking the first derivative, you can derive this centroid of the Gamow peak as 1.22 square of the charges of two entities involved in the reaction, reduced mass of the system and mega kelvins. If you use in mega kelvins, the centroid is in terms of keV. Alright. And for better understanding, I will discuss some of the reactions as an examples. Okay. For example, starting with the fundamental nuclear reaction, proton plus proton, E naught you see 5.9 keV. Here I must tell you to correlate with what I have said earlier. Coulomb barrier is 550 keV, and earlier we have seen while discussing the effect of tunneling, even at 1 keV the probability of tunneling is 10 to the power of minus 10. It is small of course, but there is a finite probability for fusion to take place at low energy. I mean 100 times less than the temperature corresponding to the Coulomb barrier. Now the centroid energy is 5.9 keV. Okay. Now I increase the target target charge. Okay, nitrogen 14. You see E is not is increasing. Now I am increasing the projectile charge from proton to alpha. Okay, it is 56 keV, and I am increasing both the charges of both the target and projectile. It is 237 keV. Alright. So the centroid of the Gamow peak increases with increasing the charge of target and projectile. This you have to understand, and this number helps you to get convinced with this statement, because this is one of the questions, how centroid of the peak changes with the charges of target and projectile. Now you remember E naught is less than Vc, that means Coulomb barrier, unless it reaches very high temperature, right. So except at high temperature, it is because of the tunneling the fusion is taking place. Alright. This diagram should help you to understand the relation between Gamow peak centroid and temperature in gigakelvin. You see ruthenium plus alpha, nickel plus alpha, calcium plus alpha, silicon plus alpha, neon 20 plus alpha, carbon 12 plus alpha, lithium 6 plus alpha and alpha plus alpha. For this case you can see that, and for here also for protons and here for alpha particles you can see. Can you see some circles here? I am drawing with red pen. This is a Coulomb barrier, okay, Vc, somewhere here at 10 gigakelvin, right, near 10 gigakelvin. Below this Coulomb barrier corresponding temperature, the Gamow peak energy centroid is decreasing with decrease in the charges. So for different reactions induced by protons and alpha, this picture should help you in understanding the relation between E naught and the charges of target and projectile. Okay. So in today's lecture, I have covered the importance of astrophysical S-factor. It is the less dependence on energy of the system, and this less dependence on the energy of the system helps us to come up with better estimate on the values of the cross section during extrapolation. If you do direct measurements, there is no point in going for the extrapolation business, but most of the measurements have been carried out by doing the extrapolation. I mean initially whatever energies are available, you do the nuclear reactions and measure the values of cross section and S factor, then you do the extrapolation. To reduce the uncertainty in the cross section value, one has to go for the S factor. Then I have considered the concept of Gamow peak. The centroid of the peak is the most effective energy at which nuclear reactions are taking place within the stars when we discuss the charged particle induced reactions. And then I have shown you how the target charge and projectile charge decides the value of the centroid peak. Okay. And in the next lecture, I will discuss more features of this Gamow peak and some more points in the next lecture. I hope you are following what I am trying to convey in the lectures. Thank you so much for your attention.